Good day, my name is Dusty, and today we are going to talk about vectors. So some quantities, such as length, area, and temperature, are determined by a number, which is called the magnitude. Such quantities are called scalar. On the other hand, to describe the displacement of an object, two numbers are required, the magnitude and the direction. Similarly, while describing the velocity of a moving object, we discuss the speed and direction of travel. Quantities such as displacement, velocity, acceleration, and force that involve magnitudes as well as direction are called direct quantities. One way to represent such quantities mathematically is through the use of vectors. A vector in a plane is a line segment, that is, it has a magnitude and length with an assigned direction. The vector AB has an initial point A and an end point B. Its magnitude is denoted by the length of AB, shown as follows. Two vectors are considered equal if their magnitude and direction are the same. All of these vectors shown are all the same. To understand this better, think about a vector as a displacement. No matter how I get from one point, initial point, to the other, end point, or where those points are, my displacement is the same. So now that we've learned about this new creature, the vector, let's talk about how to add them and subtract them and scale them, et cetera, et cetera. So sum of vectors. So definition of vector addition. If u and v are vectors positioned so that the initial point of v is the terminal point of u, then the sum u plus v is the vector from the initial point u to the terminal point v. And just as a side note, sometimes you'll see u written like this, kind of like with a bold font. Like here. And other times you'll see u written with an arrow over the top or a full-on arrow. All of these are meant to represent a vector. So it's difficult to draw a boldface U. And so usually, at least by hand, we stick to the arrow notation. Continuing on. To find the sum of two vectors geometrically, do the following. So we have a couple of choices. So one is we can use the triangle law. So sketch vectors equal to the ones you need to add with the initial point of one at the terminal point of the other. So to find the sum of two vectors geometrically, do one of the following. So A, use the triangle law. So sketch vectors equal to the ones you need to add with the initial point of one at the terminal point of the other. So by this I mean the initial point of one, this is the second, lines up with the initial point. So notice there's that initial point of V lining up with the terminal point right here of U. So terminal point of U, initial point of V. And so our sum, U plus V, would start at the very first point and end at the end of U plus V. Alternatively, we can add vectors graphically by using the parallelogram law. So we sketch vectors equal to the ones we need to add, starting at the same point, and we create a parallelogram law. Parallelogram and its diagonal is the sum. So here is our u vector and our v vector, and notice they're starting in the same place. And then I'm going to stick another u at the end of the v, stick another v at the end of the u, and I created a parallelogram, and this hypotenuse is the u plus v that I want for my sum. So let's look at a couple of animations to help us better see this. Okay, so here we have two vectors, u and v. And if we want to use the triangle rule, notice that what we're going to do is we're going to take our v vector and we're going to tag it on to the end of the u. So the initial point of v is at the terminal point of u. We move that terminal point, the sum will of course change. And our resultant vector, u plus v, starts at the initial point of u and ends at the terminal point of v. So that's the triangle rule. Parallelogram rule does the same thing, but notice now u and v are going to start in the same place, and then you sort of tack on an extra v at the end of u, an extra u on the end of v, and the u plus v is kind of the diagonal of the parallelogram, if you will. So again, here we're focusing in on the parallelogram rule. So notice you can change your u vector and your v vector. And what I want to point out is that here we go from a graphical interpretation, same diagram as before, to a geometric interpretation where the x coordinate of the sum, if u is u1 v1 and v is u2 v2, sorry, did I do that right? u1 u2, pardon me, and v1 v2, then the resultant vector would be the sum of the x coordinates, so u1 plus v1, sum of the x's, and then the y coordinate would be u2 v2, the sum of the y coordinates. So in example 1, we want to sketch u plus v, and so we can sketch our little u vector. And then we can tag on a v vector. Notice this is my attempt at the same as the u and the same as the v, trying to be parallel. And then we can go from the initial point of u to the tip of v. That will be our u plus v. Just like we can add, we can also multiply vectors by a scalar. So definition of scalar multiplication, if c is a scalar and v is a vector, then the scalar multiple cv is the vector whose length is c times the length of v, and whose direction is the same as v if c is greater than 0 and opposite to v if c is less than 0. If c equals 0, or the v is the 0 vector, then cv equals the 0 vector. And again, notice this is the 0 vector in the 0 vector. So if we have some vector v, notice that 2v is exactly twice as long in the same direction. Half v would be half the length. Negative v would be the same length, but notice that the direction is opposite, etc., etc. Okay, same thing. So here's our v vector. That's the long black one. So a half v would be half the length. Negative 2 v would be the same along the same line, but twice as long in the opposite direction. 2v, twice as long, same direction. 3v, 3 times as long, same direction. So you can see how c is just going to scale up or scale down. And notice that you could even get a 0v right in the middle. So let's talk about the difference of vectors. So the difference of two vectors, u and v, is defined by u minus v equals u plus negative v, where negative v is equal to -1, the scalar, times v, the vector. And it's the vector that has the same length as v, but opposite direction. So to find the difference geometrically, we could use the parallelogram. So notice that here's our u vector. V goes this way, negative v goes the other way. And so we can imagine tagging the two vectors on top of each other. Okay, and so u minus v is going to be this resultant vector that starts kind of at the tip of the negative v, the initial point of the negative v, and is going to end at the negative v plus u ending point, like that. Once again, let me show you an animation with this. So if I want to find subtraction using the triangle rule, you could start with your u, go along your u, and then I could basically tag on a negative v. So notice my v is going in the opposite direction as the v that's given. So negative v, opposite direction of v. So u plus negative v. Or if I used the direct approach, I could take, here's positive v, here's positive u. And so I could go u, or so I could add on take my u, and I could take away the v part of it. Minus v, u minus v. I think there's a mistake in this animation. Interesting. So let's stick with this triangle rule or the parallelogram rule, where you go along the u and then you, from the tip, go the opposite direction of the v. So let's stick with that direct approach, or that triangle approach or the parallelogram approach. So if we want to sketch 2u minus v, and we're given this u and this v, then you could imagine starting by drawing two little u's together, 1, 2u. So here's your 2u. And then tag on a v parallel to the original v. Maybe it looks like something like that. And the sum here will be the 2u. Well, this is 2u plus v. And if we wanted to go 2u minus v, we would just add on a negative v. Here's plus v. Here would be negative v. And so here would be 2u minus v, which is what we were asked for. For some purposes, it's best to introduce a coordinate system and treat vectors algebraically. If we place the initial point of a vector A at the origin of a rectangular coordinate system, then the terminal point of A has the coordinates of the form A1, A2, or A1, A2, A3, depending on whether our coordinate system is in 2 or 3 dimensions. So, for example, for this vector, A, you can see that the x-coordinate is at A1, the y-coordinate is at A2. In 3 dimensions, notice that your x-coordinate is at A1, your y-coordinate is at A2, and your z-coordinate is at A3. These coordinates are called the components of A, and we write A as equal to A1, A2, or A equal to A1, A2, A3. We use this notation A1, A2 for the ordered pair that refers to a vector, so as not to confuse it with the ordered pair A1, A2. Again, notice that we're using the angle brackets versus parentheses. So angle brackets tell you that you've got a vector. Parentheses tell you you've got a point. So for instance, the vector shown in figure 12 here, okay, are all equivalent to the vector OP equal to 3, 2, whose terminal point is at point 3, 2. So here's starting at the origin, going out to 3, 2, and notice that all those other vectors are the same. They're parallel with the same length, the same direction. What they have in common is that the terminal point is reached from the initial point by a displacement of 3 units to the right and 2 units upward. We can think of all these geometric vectors as representations of the algebraic vector A equal to 3, 2. The particular representation OP from the origin to the point P, which is 3, 2, is called the position vector of the point P. So the position vector starting at the origin. In 3 dimensions, the vector A equal to OP equal to A1, A2, A3 is the position vector of the point P, A1, A2, A3. See figure 13. This is down here. So let's consider any other representation AB of A, where the initial point is at x1, y1, z1, and the terminal point is at B, x2, y2, z2. Then we must have x1 plus a1 is equal to x2, y1 plus y2 equals, y1 plus a2 equals y2, and z1 plus a3 equal to z2. Whew. And so a1 equals x2 minus x1, a2 equals y2 minus y1, and a3 equals z2 minus z1. Thus, we have the following. So given the points A equal to x1, y1, z1, and B, x2, y2, z2, the vector A with the representation AB is A equal to, and you'll notice that what you have here is the difference. So A is equal to the difference in the x values, comma, the difference in the y values, comma, the difference in the z values. It looks complicated. It's not actually that difficult. Just give it a little bit of time. So let's do an example. I think this should make it clear. So if I want to find the vector represented by the direct line segment with initial point 2, 4, -3 and terminal point -1, 2, 1. So example 3. Let's find the vector represented by the direct line segment with initial point 2, 4, -3 and terminal point -1, 2, 1. So let's call the initial point A and the terminal point B. And so we're looking for the vector from A to B. So I list the A first and then the B with a little arrow over the top to say it's a vector. And then this is going to be equal the values of the terminal point minus the values of the initial point. So if we let all the A's be yellow and all the B's be green, this is going to be the final point, the terminal point, minus initial x value. The y value in B, which is 2, minus the y value in A, which is 4. And the z value in B minus the z value in A. Let's get some color in here. So I'm doing green. And then each time I'm taking away the yellow. Final minus initial, which I could combine to be -3, -2, 4. So there is the vector that we're looking for. The magnitude or length of the vector v, also written as v, notice, you might say, well, what's the difference? Here, it's not bold. Difficult to draw by hand, is the length of any of its representations and is denoted by the symbol like an absolute value or as follows, or with a double bar with the v inside it. By using the distance formula to compute the length of the segment OP, we obtain the following formulas. So the length of a two-dimensional vector is the square root of a1 squared plus a2 squared. The length of the three-dimensional vector a1, a2, a3 is magnitude of A equal to the root of the quantity a1 squared plus a2 squared plus a3 squared. Again, the key thing to remember here is that we're using the distance formula. So this is, or the Pythagorean theorem. This is not meant to be difficult. It's just the square root of the sum of the squares. Let's look at an animation of this. Okay, so here is a vector P and a vector, or point P and a point Q. And if we want to find the length of this vector, then all we're doing is looking for this length of this hypotenuse, right? And how would you do that? Well, we'd find the difference in the x's and square it, difference in the y's, square it, difference in the z's, square it, and take the square root of that full sum. And that would give us the length of this hypotenuse. It's just the distance formula. Easy peasy. To add, subtract, or find scalar multiples of a vector, perform the operations component-wise. That is, if A is equal to A1, A2, and B is equal to B1, B2, then A plus B is the sum of the A's, A1 plus B1. Sorry, I should say the sum of the X components, A1 plus B1, comma, the sum of the Y components, A2 plus B2. So here's your X components that are being added. Here's your Y components that are being added. Or if you want to find the difference, once again, you would find the difference in the X components and the difference in the Y components. Or if you want to scale it up, you would just multiply the X component by the scalar C and the Y component by the scalar C. There are similar formulas for three-dimensional vectors. So A1, A2, A3 plus B1, B2, B3 is equal to A1 plus B1, that's the sum of the X's, A2 plus B2, that's the sum of the Y's, A3 plus B3, that's the sum of the Z's. A1, A2, A3 minus B1, B2, B3, that's A1 minus B1, the difference in the X's, A2 minus B2, the difference in the Y's, A3 minus B3, the difference in the Z's. C times A1, A2, A3 would be CA1 plus CA2 plus CA3. That is, multiply the scalar by each component. Whew. If U is equal to 0, negative 3, 4, and V is equal to 2, negative 1, negative 2, find the following. This is example 4. So if I want to find the magnitude of the vectors, I'm just going to use the distance formula. So looking at vector U, and so I can find 0 squared plus negative 3 squared plus 4 squared, which would be root 25, or just 5. So the length of vector U is equal to 5. If I wanted to find 5 times V, this would be 5 times 2, negative 1, negative 2, which would be the same as 5 times 2, comma, 5 times negative 1, comma, 5 times negative 2, or 10, negative 5, negative 10. I wanted to add the two vectors. This would be saying U, which you may recall is 0, negative 3, 4, plus V, which is 2, negative 1, 2. So this would say add the X components, so 0 plus 2, negative 3 plus negative 1, and 4 plus 2, which is just 2, negative 4, and 6. And in case you're wondering, no, you don't need to show all this work on your homework. I want to find U minus V. U minus V would be U 0 minus 3, 4 minus 2, negative 1, 2, which would be 0 minus 2 -3 minus -1, and 4 minus 2, which is a funny way of writing -2, comma, -2, comma, 2. And again, we know it's a vector because we're using the angle brackets. In E, we want to find 3u plus 2v. So this would be equal to 3u, which is 3 times 0, -3, 4, plus 2 times v, 2, -1, 2. I think this is a -2. Pardon me, I got to come back and fix the previous one. This would be a -2 right here, which would make this 4 minus -2, so this would make this a positive. And 4 plus 2 would be 6. Sorry for losing track of that sign. I did the same thing previously, didn't I? In C, this should be negative. This should be negative, which would make the Z component -2, or 4 plus -2, which would just be 2. Sorry, that's a copy error from the previous page, not a math error, if you will. So back on track. So if we want to find 3u plus 2v, that would be 3 times 0, -3, 4, plus 2 times 2, -1, -2. And then we can multiply each of the components of the first vector by 3. So we'll have 0, -9, and 12, plus each of the second components of the second vector times 2. So 4, -2, -4. And then we can add 0 plus 4 is 4. And then we have -9 plus -2 is -11. And then we have 12 plus -4 is going to be 8. Something like that. Very good. Example 5. Find the component form and length of the vector with initial point P, -3, 4, 1, and terminal point Q, -5, 2, 2. So we want to find the component form of the vector that starts at P and goes to Q. And so this would be just the vector formed by looking at the difference where we start at the Q and we take away the P. So let me write it out and then I'll color what I'm doing. So I take Q minus P at each point. So Q, -5 minus P, which is -3. So this is yellow minus blue, comma. Then for the Y's, start with the Q, the end point of 2, and subtract out the P Y value, which is 4. Let's start with the yellow, subtract out the blue. And then for the Z's, same thing, start with the 2 from the Q, subtract out the 1 from the P, start with yellow, and with blue. And so the components of vector PQ are -5 plus 3, or -2, comma 2 minus 4, -2, and then the Z's 2 minus 1, or 1. example 5, or example 6, pardon me. A small cart is being pulled along a smooth horizontal floor with a 20-pound force, making a 45-degree angle to the floor. What is the effective force moving the cart forward? And there's a hint, the effective force is the horizontal component of the force F. So let's draw a little picture. So we have our cart. Okay. Supposedly there's probably wheels on it because we don't really want to deal with friction. And then there's a 20-pound force. So we need a 20-pound force. And that 20-pound force is going to be at an angle of 45 degrees. 45 degrees. So here's our 20-pound force. It's 20 pounds at a 45-degree angle. And the question is, what is the effective force moving the cart forward? And so what I want to point out is that if you're pulling at an angle, then some of your force is pulling up and some of your force is pulling over, right? Or if I phrase it another way, some of that force is horizontal and some of that force is vertical. Maybe we could call the horizontal part Fx and the vertical part Fy. These are both vectors. So that horizontal part plus the vertical part together form the overall force. Okay. Since we're pulling at an angle of 45 degrees, it should be pretty reasonable to think that the magnitudes of Fx and Fy are the same, right? Like common sense would say if these guys have the same magnitude, but we'll see that shortly. You should also be able to see that there's no y in the in Fx and there's no x in Fy. So if our vector F has an AB, has an x component A and a y component B, it should be clear that your A is going to be Fx and your B is going to be Fy. And we also know that or I should say that these are the magnitudes, not the vectors. Okay. And we already decided that these two magnitudes were equal, kind of based on symmetry. So in other words, our vector F is almost like an AA, not AB, because it's got the same x component and y component. So how can we use this? Well, we know that the magnitude of this vector is going to be 20. And so let's find the magnitude of a vector that has the form AA. So the magnitude of AA vector would be the square root of a squared plus a squared, or a times the square root of 2. And we're thinking this is equal to 20. Okay. So if 20 is equal to a times square root of 2, because a squared plus a squared is 2a squared, pull the a squared out as an a, then we should see that a is equal to 20 divided by square root of 2. Which tells us, put all this stuff together, this tells us that fx is equal to 20 over root 2, but that's the x component. The y component will be 0. And the question is, what's the effective force of the horizontal component? And so our answer is the effective force is 20 over root 2 pounds in the horizontal direction. We denote by V2 the set of all two-dimensional vectors, and by V3 the set of all three-dimensional vectors. Just to note, this is a big V, like a capital V2 and a capital V3, versus the lowercase v's that we were using earlier. More generally, in subsequent math courses, we will consider the set Vn of all n-dimensional vectors. An n-dimensional vectors is an ordered n-tuple, a equal to a1, a2, dot, 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 an, where a1, a2, dot, 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 an are real numbers that are called the components of A. Addition and scalar multiplication are defined in terms of the components, just as for the cases of n equals 2 and n equals 3. So there's a number of vectors, there's a number of properties of vectors. These should be easy to use. Don't sweat about memorizing these properties. You should just be able to pick them up pretty easily. So if A, B, and C are vectors in Vn, and C and D are scalars, then A plus B equals B plus A, commutativity of addition. A plus 0 equals A. Please note this is the 0 vector. 5, C times A plus B equals CA plus CB. 7, if you multiply the scalars, CD times A, you get C times DA. Now working down the second column, 2, A plus the quantity B plus C is equal to the quantity A plus B plus C. So that's the associative property of addition. In 4, A plus negative A is equal to 0. Again, these are vectors. So A, B, C, and 0 are all vectors. C plus D, that quantity times A is CA plus DA, and 1A is equal to A. Basically, vectors work the way you would expect them to work with addition, subtraction, and scalar multiplication. No surprises. We'll get some surprises in the coming sections. 3 vectors in V3 play a special role. So we're going to let the vector I equal 1, 0, 0. So that's the a vector with length 1 in the x direction. We're going to let j, or the unit vector j, equal 0, 1, 1. This is a vector with length 1 along the y-axis, pointing in the direction of the positive y-axis. And we'll let k equal 0, 0, 1. This is a vector with length 1 pointing along the z-axis in the direction of the positive z. So these vectors I, j, and k are called the standard basis vectors. They have length 1 and point in the directions of the positive x, y, and z axes. Similarly, in 2 dimensions, I equals 1, 0, and j equals 0, 1. Let's look at a manipulate before we go farther. So notice that we can think about 4 along the x-axis as being the same as 4i here. And you can think about whatever your length is along the y-axis, maybe the v2 equal to 3. This is the same as if this is j, so 3 in the y direction would be 3 j's, j, j, j. And so 4, 3 is the same as 4i plus 3j. So as we just said, any vector can be written using the standard basis vectors. So here you can think about the vector where you have a1 and a2. You can think about that as a equal to a1, the component. This is just the component in the x direction times I. That's what gives it the length. And then you can take it times a2. That's the component in the y direction times j. That's what gives it the direction. So together, a1i plus a2j. This is going to give us an alternative way of writing our vectors. So prior we were just using the angle brackets. So we would say a1, a2, a3. Now we have a new way of writing a equal to a1i plus a2j plus a3k. Means the same thing, it's just a different notation. So let's do an example of this. So we want to, in example 7, express the following vectors in terms of the standard basis vectors. And so in A, we have 5 minus 2, 6. This would be 5i minus 2j plus 6k. And in B, we have 4j minus 2u, where, 4v minus 2u, where v equals 2i plus 6j minus k, and u equals j plus 3k. So if we follow along, we're saying that 4v minus 2u, this would be 4 times v, 2i plus 6j minus k, minus 2 times u, j plus 3k. So now we can just distribute. We're just doing algebra kind of old-fashioned style. We have 8 i's plus 24 j's minus 4 k's minus 2 j's minus 6 k's. Or how many i's altogether? We have 8 i's, 24j minus 2j, so plus 22j minus 4k minus 6k minus 10. A unit vector is a vector whose length is 1. For instance, I, j, and k are all unit vectors. They have length 1. In general, if a isn't 0, then the unit vector that has the same direction as a is u equal to 1 over the magnitude of a times a, or a over the magnitude of a. So for example, if I want to find a unit vector v in the direction of the vector from p 1, 0, 1 to q 3, 2, 0, I would proceed as follows. So I first need to find the vector from p to q. So start with the p, go to the q, draw the little arrow over the top. And now we're going to find the difference in components. So again, I'm going to start with the yellow q, and I'm going to subtract out the blue p. We've done this a couple times, so maybe I won't write out the work. So 3 minus 1 for the x component is 2. And then 2 minus 0 for the y component is 2. And 0 minus 1 for the z component is negative 1. 3 minus 1, 2 minus 0, 0 minus 1. So this is the vector from p to q. Our question's asking us to find a unit vector v in this same direction. So the next thing we need is we need the length of PQ. So the length of vector PQ is the square root of the sum of these squares. So 2 squared is 4, 2 squared is 4, negative 1 squared is 1. So the length of this vector is 3. This tells us that our unit vector v equals 1 divided by 3. So this would be the 1 over 3 coming from that 3 there, times the PQ vector, 2, 2, negative 1. If you wanted to put this all together, you'd have 2 over 3, 2 over 3, negative 1 over 3. And both of these results would be okay. Both okay representations. I'd like to take a little time out and share a historical note. So the first mathematician to present a detailed theory of spaces of dimensions greater than 3 was Hermann Grassmann. There's a typo here. Greater than 3 was Hermann Grassmann. Grassmann was born and lived for most of his life in Stettin in Pomerania, now Poland. Although at the University of Berlin, he mostly studied philology and theology. After leaving the university, he returned to Stettin to pursue work in mathematics and physics to prepare himself to pass the state exam for teachers in those subjects. He subsequently taught briefly at a Berlin technical school and after 1836 at various schools in his hometown. His great ambition in life was to qualify for a university position. That is, he wanted to be a professor. But although he developed the ideas of the theory of vector spaces, few people read his efforts or recognized his great originality. Grassmann sent copies of his book to several influential mathematicians, but the only one who commented favorably on it was Hermann Henkel, a student of Riemann's, who planned to include some of Grassmann's material in his own books on complex variables. In the 1860s, Grassmann turned his attention to the subject of languages and made some important scholarly contributions to the study of Sanskrit. His later mathematics works, however, were of lesser quality, and he never attained his goal of a university professorship. His goal was to be a math professor. He created stuff that we're talking about today, but he never got to be a professor. And I think we're going to pick up his history a little bit in a subsequent lesson. Example 9. If v equals 3i minus 4j and is a velocity vector, express it as a product of its speed times a unit vector in the direction of motion. So let's find these things. So if we want to find the speed, this would be the magnitude. So we could just use the letter v here, not a vector v, and it would be the magnitude of vector v, which is the square root of 3 squared plus negative 4 squared, which is conveniently square root of 25 or 5. So our velocity of vectors is given. The speed is just 5. In this case, no units because it's a math class. Maybe it's in meters per second, something along those lines. And so our unit vector would be 1 over 5 times 3i minus 4j, or 3/5 times I minus 4/5 times j. And so the question asked us to write this as a product of speed times a unit vector in the direction of motion. And so our answer is going to be that v, the vector, is equal to 5 times 3/5 I minus 4/5 j. And so speed is here. This is the 5. And then a unit vector in the direction of motion is this guy right here. So we have answered the question. Let's look at an application that I learned, or at least begin an application that I learned the hard way. So here's a preliminary application or example of an application that I learned about the hard way. So a roof valley is where two roof planes meet. So here would be one roof plane. Here would be the other roof plane. And the roof valley is this spot right here where the two planes come together. Further, the pitch of a roof steepness in the US is generally given as a ratio such as a 412 pitch, which means that the roof has a rise of 4 inches for a run of 12 inches. So we would describe a roof like this as having a 412 pitch. The second number is always given as 12. It's just the way it works in America. Example 10. Suppose one plane of a roof has a 612 pitch, that is 12 over and 6 up, and it is intersected by a second plane that has a pitch of 412, that'd be 12 over and 4 up. What is the pitch of the valley where the two planes meet? So let's start by drawing a picture similar to the one above. So we've got the first plane. Let's imagine it's like an infinitely long plane, and it intersects a second plane, something like this. And we have a valley, which notice could be a ridge as well, where the two meet. Let's suppose that the left plane has a pitch of 612, and the right plane has a pitch of 412. So 612 means 6 up, 12 over. 412 means 4 up and 12 over. And our question is, what's going on along the pink ridge line? So for the sake of simplicity, imagine that these roofs are infinitely long. Okay. And so suppose you start down here at the gutter where the two come together, and you marched horizontally into the middle of inside the roof a length of 12. And then you came up to the ridge line here. So there's your 90-degree angle. So we went over 12, and so we would come up 6. And you could think about that as being represented by a vector like 12 in the horizontal, on the x component, no y's in this case, and then we're going to go up by 6. Okay. And then we could try to figure out, well, what happened the other direction? Well, the question is, if we went along the horizontal, how far would we have to go up 6? Well, let's think about it. If I went here and I went out 12, and then I come up 4. Wait, I haven't gone up far enough. So I have to keep going out. How much farther do I have to keep going out? To keep going out another, I think 6, to come up another to go up another 2. And so altogether, we've gone out a total of 18 to go up by 6. This is 6, then the distance along the horizontal must be 18. So we have 0, because it's going, this roof plane is perpendicular, 0, 18, and 6. I don't need a 6 in the end. So together, these are getting me to that end point. So I have 12 along the horizontal, don't go any in the y direction, then go up 6. to get to that same, to continue on to figure out where I would be on the other plane, I wouldn't go any farther in the x direction, but I'd have to go 18 in the y to have made it up a height of 6. So together, these combine to say that the valley is along the vector 12, 18, 6. Right? Because it would take me 12 in the x direction to go up 6. It would take me 18 in the y direction to go up 6. So if I want to go up 6 along the valley, I've got to go 12 in the horizontal and in the x direction and 18 in the y direction. So now all we got to do is figure out how to write this as a pitch. So to do this, we're going to try to find a unit vector. But it's kind of a special unit vector. What we want to figure out is we want to make sure that we want the horizontal distance to equal 12. Okay, and so it's not quite a full-on unit vector here. We got to do something a little bit modified. So we got to say, how far have we gone in the horizontal distance, like along the flat part? And that would be travel the total distance of 12 squared plus 18 squared. That'd be square 144 plus 324, or square root of 468. This is how far we've traveled, like this distance right here. Okay. And so if we want to make that distance a length of 12, we want to figure out what vector we're working with. We would need to figure out our valley, give our valley a length of 12, divide by that 468 to make sure the length is perfect. It's 12, 18, 6. And this should give us a horizontal distance of 12 and a vertical distance of some number. So our pitch is going to be the vertical distance right here, the 6. 6 times 12 over 468 under the radical, 12 pitch. Or if we multiply all that out, 6 times 12 divided by square root of 468. This would be like saying we have a 3.33 12 pitch. So if you've ever been on a roof, this will resonate, that the easiest, safest spots, flattest spots, if you will, to walk are in those valleys where it feels actually less steep than both of the planes on either side. So you had 412 on one side, 612 on the other, and right there in the valley, it's about 3 1/3 12 pitch. Yay. So example 10, a jet airliner flying due east at 500 miles per hour in still air encounters a 70 miles per hour tailwind blowing in the direction 60 degrees north of east. The airplane holds its compass heading due east, but because of the wind, acquires a new ground speed and direction. What are they? Well, let's start by drawing a picture and remembering how a compass works. So we know that we have north, south, east, and west. And so our jet airliner is flying at 500 miles per hour due east, or in vector form, this would be 500, 0. And then we know that the wind is coming 60 degrees north of east. And so we want to go from that east vector, we want to come up 60 degrees. And we know it's a shorter vector and it's at 70 miles per hour. And so we want to know what happens when we combine the red wind vector and the black jet vector. So in order to do this, we're going to need to find the components of the wind vector. So one of the pro tips is that if you start from the positive x-axis and measure your angles counterclockwise, then you get to find your x component using the cosine function and your y component using the sine function. So we know that our wind vector, is going to equal 70. That's going to be the magnitude. Times the x is going to be the cosine of 60 degrees. And the y is going to be the sine of 60 degrees. Or cosine of 60 is a half. Sine of 60 is √3/2. So all told, we know that our wind vector is going to be 35, and it looks like 35√3. So if we combine our jet vector and our wind vector, we will get jet plus wind equals, looks like we'll get 535, 35√3. And then the question asks, what is the new ground speed? What is the new direction? So the ground speed is the magnitude. Pardon me. Which has magnitude √535 squared plus 35√3 quantity squared, which is about, according to my Texan friend, which is about 538.4. 538.4. So this means that the ground speed equals this 538.4 miles per hour. To find the angle or the direction, we can simply use our arctangent. So our arctangent of the opposite, the y, over the x, the adjacent, which would be arctangent of 35√3 over 535, which, double checking to make sure I'm in degrees mode, is, let's see, 35 √3 divided by 535 is about 6.5. Which would be 6.5 degrees north of east. Heading north of east. So that should make sense to us if you think about the context of the question. The jet's going at 500 miles an hour. So even though that's a stiff wind, and is certainly blowing it a little bit to the north. It's pretty small relative to the to how fast the jet's going. So it's going to blow it a little bit farther north, 6.5 degrees, but not a lot north of east. Very good. So example 11, Lisa and Rose exercise at CrossFit. One of their trainings is to pick up a 500-pound weight together for a few seconds. Lisa is shorter than Rose, so they feel different amounts of tension on their arms. Use the figure to find each tension. So these are pretty fit athletes, especially given the angles that they are lifting at, as we shall soon see. So we have T2 must represent Rose, and T1 must represent Lisa. I'm saying this because of their heights. Okay. And then, of course, you have the weight that's 500. And since we're learning about vectors, it should be pretty clear that we need to represent each of these points in terms of a vector. So the 500 pounds down has no x component and is going down. So it's negative 500 in the y direction. The Rose vector has some unknown magnitude of T2, but we know how much the ratio between the x and the y using trig, I think like we did in the last example. So we know that our x component is going to be cosine of 62 degrees. So that's 62 degrees measured counterclockwise from the positive horizontal axis, positive x-axis, and then sine of 62 degrees. And so this is the 62 showing up there. And again, you've got x is going to be cosine, y is going to be sine. And again, our angles are measured from the positive x-axis. So then things get a little bit more interesting on the next part for T1, because we're given 40 degrees from the negative x-axis, which would have to be 140 degrees from the positive. So T1 could be written as T1, this unknown magnitude, times cosine of 140 degrees, comma, sine of 140 degrees. And because at the moment that we care about, nothing is moving, right? There's sort of like that instant when they're picking things up. This is sort of a static bit. We know that the sum of these forces must be 0. And so what we can do is we can add up, here was that 140 degrees. What we can do is we can add up the x components and know that the x components must equal 0 and the y components must be equal to 0. So again, at equilibrium, the sum of the forces is 0. Okay. So if we look at the x components here, let's see, what color should we use? So if we look at the x's, so we have x, x, and x. So you get magnitude of T1 cosine of 140 plus magnitude of T2 times the cosine of 62. Plus 0 equals 0. And like, what's the 0? What's that first 0? That first 0 is the 0 from below. Okay. And then if we look at the y components, sum of the y components must be 0. So these are the y's. And so if you look at the sum of the y's, you'll get that the magnitude of t1 times the sine of 140 plus the magnitude of t2 times the sine of 62 degrees plus negative 500 equals 0. And so you'll notice that there's two equations here and two unknowns. And so we can solve this using a matrix. So to solve this using a matrix, I'm going to skip ahead to the next page and teach you a little bit about how to do that, and then we'll come back and finish this example. So let's look ahead to page 10. So in the last couple of examples, one of which is still in progress, we've had to solve systems of equations. An efficient way to do this is to use a calculator involving matrices. And so here you have instructions for creating a matrix, which involves the matrix command on the calculator. So I'm going to hit matrix is right above the reciprocal button. So second matrix, and then an arrow over to the edit, and then enter to edit the first matrix. And you can add, divide, or multiply two matrices, add, subtract, divide, or multiply. Just a note that when I say divide, that's a little bit of a misnomer, because there isn't division per se with matrices. There's actually what's called a matrix inverse. And this is going to be a big theme in linear algebra. But what we actually care about here is solving linear equations using matrices. And so we would create a what's called a coefficient matrix. And again, you're going to learn about this in linear algebra, and solve it. So if we have these two equations, x plus y equals 1800 and 20x plus 40y equals 4200, for example, what we notice is that the coefficient, or we can create a coefficient matrix by taking the coefficient 1 and putting it in that first spot, coefficient 20 and putting it in the second spot. 20 showing up here. Got 1 in this third spot, which is actually the first row, second column, and 40 is going to show up in the 2-2 position, second row, second column. And then we have the first equation is equal to 1800. So in the last column, first row, I'd have 1800, and we've got 4200 for what the second equation is equal to, expression is equal to. And so in the 2-3 position, second row, third column, we'll have 4200. So this is what's called a coefficient matrix. And what this is telling you, for example, in the second equation, is that it's saying 20x plus 40y is equal to 42,000. I think I said 4,200 earlier. I meant 42,000. So the good news is once we have this entered into our calculator, we can go back to our home screen and use this command rref, where the instructions are on the second line. So we'd press matrix and then math, and then we arrow down until we find rref, press enter, and we go matrix and arrow down, find the one we want, probably like matrix A. In this case, it's matrix A. And then we press enter. And the cool part is we start here and then we end with this new reduced row echelon form, 1, 0, 1500, 0, 1, 300. And what this is telling us is that 1x plus 0y equals 1500. X equals 1500. And it's telling us that 0x plus 1y equals 300, or y equals 300. That's what this result is telling us. So it did all of the beginning algebra solving of a system of linear equations for us. So let's see how this works in solving the previous example. So I'm going to create a matrix here. So create a coefficient matrix. Notice that in the last question, the unknowns were x and y, but here the unknowns are t1 and t2. Those are our x and y. And so our matrix is going to be cosine 140 here to there, and then sine, and then cosine 62, and this is going to be equal to 0. There's no equal sign, you just have the 0. And then the second line is going to be sine 140 sine of 62, right? So this is about the y coordinates being equal, and it's going to be equal to 500. So I'm going to move, I have to move this 500 here to the other side. So that's why it's positive. Okay. So just so you're seeing where things are coming from. Cosine 162 is there, sine of 140, and sine of 62. Okay, that's where everything's coming from. And then we're going to use the RREF command on our calculator. And let's see what we get. So I'm going to just take a moment and put this in the calculator. So I have a 2 by 3 matrix and cosine of 140 degrees and cosine 62 degrees, 0, and the sine of 140 degrees and the sine of 62 degrees, 500. And then I go back to my home screen. So I go matrix, math, RREF, which is option B. Then I got to choose the matrix to work on. So I go back to matrix, and the name I want is A, and parenthesis and enter. And I get 1, 0. Let's call it 240 if I round to the nearest whole number, 240, and 0, 1, 362 or 392 if I again round to the nearest whole number. Okay. And so what this is telling me is it's telling me that T1, a magnitude of T1, is 240 pounds. This is a magnitude. And the magnitude of T2 is 392 pounds. Okay. In other words, if we go back to figure out which is which, we're saying that Rose lifted 392 pounds and Lisa lifted 240 pounds. Okay. And so that about wraps up this section. Now you know everything there is to know about vectors. Thanks for sticking with me through this long lesson, and hope you have a wonderful day practicing all these techniques, which you are going to find very, very helpful in this class and certainly in any physics or engineering classes that you might take. Take care.